My name's Hazim Gaber, and today I'm going to be talking about analog signals. We were talking about digital signals yesterday. We were talking about drain wires, cable twists, shielding. I'm going to look at some analog signals now because analog signals are still in existence. I don't recommend using analog systems much, but we still have fax machines and pots and uh, analog cameras and satellites. So we still have still have a lot. And in 10 years, we probably will still have a lot, even though things are being replaced. Anyway, if you went to school and you learned trigonometry, you know about sine, cos, tan, which are functions. So if we have a graph, we have a sinusoidal wave. And this is measured in 180 degrees, 360 degrees. This is also time. So we look at the height, we call it the amplitude. I'm not going to get into any complicated mathematics, but generally an analog signal looks like this graph. I'm going to draw it again though. So if I have a graph and I have a wave, this is traveling down a wire over a period of time. The height, also known as the amplitude, and then the distance of one cycle, i.e., how long does it take to complete one cycle? This is called the frequency or the period. So the time, the time that it takes to complete one full cycle is the period. And the frequency is measured in hertz. Or how many of these do I get per second? So if this was 1 second to here, and we had 2, so we have 1 cycle, 2 cycles, so we have 2 cycles per second. So the period is half a second. And the frequency is 2, because we have 2 per second. So that's seconds to the -1. Makes sense so far? So I can calculate the frequency from the period. I can calculate the period from the frequency. But how does this help us? Well, the answer is that if we wanted to use an analog signal to transmit data, we can vary the height of the signal. We can vary the period. So we call this amplitude modulation. And we call it frequency modulation. Which is what radio signals AM and FM are. So if I'm transmitting data and I do an AM, I can change the height to keep the period steady. For example, so I'm just changing. I still have 2 per second, but I've changed the height or amplitude versus FM. I keep the height the same, but I'm going to change the frequency. Now, obviously, this is an exaggeration, but the telephone signal could be around 3,000 hertz. So that means 3,000 cycles in 1 second. So the other thing we have is what we call a phase. And so I started here. But what if I started here? So now this is 90 degrees. So now I'm off. Now my signal's off by 90 degrees because it doesn't. My signal is also an angle. Whoops. So starts at 90 again here. So if we think about it, my signal is not starting at 0, starting at 90. And so we call this the phase. So we can have a phase shift in our signal, which is less important, but this whole signal can be represented by an equation. And remember our trig function, so sine 2 pi f t plus the phase. So this is the amplitude, and this is the frequency, and this is the phase. And so all we need to know is the time. So at any time we plug into this equation, we can get the value of the signal. Going back to this, I told you that the telephone was around 3,000 hertz. So radio can be 3,000 kilohertz or 3 million hertz. And a video, like an antenna, can be 3,000 megahertz or 3 billion hertz. And the radar can be 300 gigahertz, so 300,000 million billion hertz. Now, the second question we have is, say I have a guy up on the hill and he's yelling, and we're trying to listen to him. We got really big ears. How loud does this guy have to be for us to hear him? And we also have to think about, there can be noise, there might be water, there might be a bear, there might be noise from all different sources. So the louder he is, or the less of a drop in the signal, the better we are able to hear him. If he's yelling but we can't barely make out the words, then we're still receiving the signal, but we might not understand all the words and we have errors. So the same with an analog signal. If I got a pair of antennas and we have a very powerful signal here, what is the power needed to reach the antenna? And we have to factor in all the noise. And remember, this might be traveling over a cable where we can control the method of transmission. We can add a shield. Or it might be traveling throughout the air, in which case we got nothing. And we measure the power in decibels. So we want to know the decibel is the ratio of transmit power to received power, and it's measured logarithmically. And what that means is a dB of 100 or a dB of 90. Stupid thing. So a dB of 100 is 10 times bigger than 90 dB. Which sounds silly, but that's how it's measured. It's measured using what we call a logarithm. And I'm not gonna explain that in too much detail, but basically calculate a log with a calculator. It's 2021 or whatever year you're watching this in. Maybe it's 2121. I don't know. But the point is, a log is also known as a base 10. So every increase in 10 is double. So 0 decibels change means that we have no power change. A 10 decibel change means 10 times change. And 20 means 100. And 30 means 1,000. And we can calculate, through here, you can calculate 1, 2, 3, 4. So 1.3, 1.6, 2, 2.5. So what you'll do, if you're calculating the change, you might say, my signal here is 30. And my signal here was 40. So I can calculate dB of the log of 10 times 40 over 30. I mean, it'll probably drop, so maybe the signal's going this way. And it's 10 log 4/3, which is like 1.333, which is something like almost 2.0. So that means we have twice as much transmit power as we have received power. So we've lost half of our power on this transmission. And that's fine. We just gotta know how to increase the power. With increased power comes increased noise though. So if we're losing a ton of power, we can't just crank up the power forever because we'll get a lot of noise that we have to filter. And we'll also have to make sure the transmission medium can support it. And we have other things to think about. So, for example, a radio station can't just pump out as much power as it wants. You have to think about, do they even have the equipment to do it? There's government regulations and that kind of thing. So the reason we use logs is because it lets us express really big numbers without having to use really big numbers. So going back to that, from my source here, and I have recipient, I've created this signal, and we know we have noise, and we know we also have power loss. We also have an echo, because this guy might not be able to absorb signal as well as he wants to. So some of our signal bounces back, which is bad. So we have to be able to filter it. And then we also have a delay. So how much time from when, if I said hello, how much time does it take for that to be received? We call it the latency, which we're going to look at more later, but latency is a very important measurement. And if this is a cable or if it's a radio wave, it's there's not much latency, but if it's a satellite, it can have latency of like 1 or 2 seconds. And that's that.